Thanks, Josh. So hello, nodes. And yes, I hope you're having a fantastic conference so far. This presentation will be about data imports in Neo4j and how you can speed them up using concurrency. So first, a little bit about me. My name is Rob. I work at Neo4j as a software engineer in the Cypher runtime team. So our team's work revolves around query execution in Neo4j. We mostly maintain the code that executes a planned Cypher query, builds the result set, and then sends it back to the user. As well as that, I'm from the UK. I love all of these things, but especially my wife and newborn son, who is already much bigger than that photo, even though it was taken about 3 weeks ago. But enough about me. Let's have a peek at what we'll talk about today. So first, we'll look at a short story of importing data into Neo4j. We'll review some ways to make those imports go faster. We'll talk about some of the problems that you might face, especially when using concurrency, and how we'll solve them. And then we'll take a sneak peek at the future. So data import. The canonical way to import data into Neo4j using the load CSV command. Let's say we have some data in a CSV file along with some headers, some toy data here. We might write a query that looks a bit like this. So we import the data, we create, in this case, a vehicle, and we set a couple of properties on it, one of which is a calculation. You can think of the create part of this as kind of like a for loop, if that helps. So the load CSV sets up a kind of a stream that we then iterate over and execute the create once for every iteration of the loop. We end up with a graph that looks like this. 3 nodes for 3 lines. But what happens if we have more data? So let's try 1 million entries in our list and run the same query. What do we get? Nothing. So what happened? So we ran this query, and when we ran it, the database engine started a new transaction. As the query engine loops over the create line here at the bottom, it adds more and more nodes to this transaction, which increases the memory footprint of the transaction. And eventually we run out of transaction memory. Boom. So one solution, add more memory. But really, how big is our wallet? Can we keep doing that? What about a different problem? So here, if we zoom in at the top of that data set again, we can see this line here, scooter, which has 2 wheels and doors. And a reminder of the query we're running here. One of the properties is a division of 2 of those numbers in the data set. So what happens now? If you guessed divide by 0, then pat yourself on the back. Indeed, we get an error, and the transaction is rolled back again. And again, this is our graph. So what do we do? The real solution is to use more transactions. So Cypher team, a while back now, implemented call-in transactions to help us avoid these problems. So we wrap our create line in this call statement. In this case, a call statement which iterates 1 row for 1 transaction and error handling of on break. You can think of this, if this helps, I'm not sure, a little bit like a nested transaction or set of transactions inside the outer transaction, each of which can be committed or rolled back as needed. So we run that statement again, this time with call-in transactions, and we get, well, the same error. Okay, we still get a problem, but we notice that we have 2 transactions committed. And this is our graph. So we've made some progress. And in fact, what happens is because we used on error break, we told the execution engine to stop iterating those batches as soon as we hit an error. So we get through the first 2 fine, and we get our first 2 nodes, but then we get to transaction 3, we get this error, and we stop and roll back, and we don't start any more transactions after that. Other options for error handling would be on error fail, as in if anything fails, then everything fails and nothing is committed. Or we can tell the engine to ignore errors entirely and just deal with them later. And in fact, there are a whole suite of tools available in call-in transactions, including reporting status. As you can see at the bottom here, we have this status property status object, which contains several properties and some examples of what they look like there. So, to summarize, we use load CSV to import data from a CSV file. We use CONCURRENT transactions to divide and conquer the input stream. We have a few options for ways to handle the errors that we see, and we have a way to detect and mitigate those errors. But Robert, I hear you say, I've got 1 million rows to import and I've got 20 Jira tickets to reply to, and my build still doesn't pass in despite running it 4 times today already. What do we want to do? I don't have time for this. So we add concurrency. Let's make it faster. Let's say we have 500,000 rows and we execute a query that looks like this, very similar to the previous one. It takes around 7 seconds. I made this GIF earlier because I'm too chicken to do this live. And there it is, 7 seconds. So not terrible, not great. Can we do any better? With concurrency, we can use something called APOC periodic iterate. So this is a procedure as part of the core APOC library. We can run these batches in parallel, and we can select the batch size, the number of rows that we run per transaction. And this takes around 1.5 seconds, so much faster. But I don't like it. I'll tell you why. Aesthetically, at least. Not very pleasing query, is it? I mean, we have strings here being passed into a procedure. Where's the syntax highlighting? If we put this in an application, we have to use string templating. It's kind of ugly. So no, not for me. Maybe a more serious objection is that it's very opaque, especially for the Neo4j planning engine. So procedure calls are their own operator. As you could probably guess, there's a whole lot more that goes on behind the scenes to run that create statement, but we don't see it in the plan, and it makes it hard for us to optimize. Compare and contrast to native CONCURRENT transactions, which has this kind of more expressive syntax, this more expressive tree logical plan. So what do? We have created CONCURRENT transactions concurrent, native concurrency for CONCURRENT transactions. So now we can use this concurrent clause to modify slightly how we run this using native Cypher syntax. The results are pretty much on a par with APOC, with all the benefits of native Cypher. So here you can see it ran in about 1.8 seconds, just under. And here is a screen grab of me importing 10 million rows. I won't make you sit through and wait for that to import because it's taking 110 seconds. But only 26 seconds with concurrent transactions. So massive speed ups when we run these in parallel. And speaking of concurrent transactions, the way that we choose the concurrency is by providing it as an integer here. If you don't provide this, you just use the kind of default syntax, then the Neo4j engine will read the number of processes at startup and pick a value based on that. But if we're explicit and we choose, say, for example, 6 transactions, then what we'll do under the hood is we'll prepare the long list of the queue of transactions to run that we know we'll be running. We have a concurrency of 6, so you'll get up to 6 threads operating on these transactions. Each one will pick a transaction off the queue and begin working. And then in this case, we see that transaction 3 is finished, so thread 3 will commit its work and then pick the next one off the list, in this case, transaction 7. So concurrency. This throws up an interesting situation if we start performing writes of the graph. Back to our sequential, our non-concurrent query. Transactions run in order, in sequence, and you can see here transaction 1 on the left is running commits, and then transaction 2 has begun immediately after and can see all writes that were committed by transaction 1. And likewise, transaction 3, you can see the writes from transaction 2. So let's take a toy example. Say we have a graph with a single node in it. We're going to import a bunch of data, and we're going to try and link each new node that we import from this data to the existing single node in the graph. We might start with something like this and then end up on the first iteration with one node, the first node in that CSV being added correctly. But then we expect this to happen on the second iteration with the second row, but actually what happened was this. So what happened here is that the match clause from here matched not just the original node, but it's also matching the second node, the node that was committed on the first transaction. And you might be able to guess what happens on transaction 3. We end up with something that looks like this. Not very useful. With concurrent transactions, this becomes even more compounded by the non-determinism. So our running transactions have an unpredictable execution time. Any one could finish first. Let's say, for example, transaction 2 is the first to finish here. We spin up transaction 4. Transaction 4 can see the results of transaction 2, but it can't see the results of transaction 1 or transaction 3 yet because they haven't finished. Likewise, transaction 1 finishes, transaction 5 is started. It can only see the results of transaction 1 and transaction 2, but it cannot see the results of 3 or 4. And so concurrent transactions might produce a graph that looks like this, or it might produce a graph that looks like this, or any other variety that you can imagine. So more generally, we say that calling transactions concurrent uses concurrent semantics. That is to say that rights committed in the execution of one transaction may or may not be observed by the following transactions. The simplest solution here, of course, is to move the dependent clauses in your subquery outside of the inner scope and move them up here to ensure they don't match any of those intermediate changes. And we get a nice clean graph that looks like this. Let's talk about error handling. So we mentioned on error break and fail earlier. These failure modes will be slightly different in a concurrent query, mostly because of the concurrent nature. So if we go back to our example here of our 3 concurrent transactions, let's say that transaction 2 has a problem, needs to roll back. What we try to do for on error break or on error fail is ask other concurrent transactions that are in flight to stop what they're doing and roll back too. But because of the nature of non-determinism, maybe they can, maybe they can't. In this case, transaction 1, we can see managed to roll back, but transaction 3 will continue. And so we say that concurrent transactions may not be rolled back. You can think of this as a bit like a graceful stop, the difference between a sig term or a sig kill, for those of you that are familiar with Linux syntax. The most reliable solution here is to use the status var to determine whether or not transaction was successful. Another problem we can have, lock collisions. So when you introduce concurrency, locking can be a problem. So if we go back to our villages data set, but this time we're going to use a slightly different data set. We're going to have counties instead of latitude and longitude. And we're going to begin merging new loads into the graph in 2 concurrent transactions of 2 rows. Many villages can be part of one county, which will cause us a problem, as we'll see soon. So we'll execute the query. First iteration, we'll have 2 transactions, and we will create 4 nodes without any collisions. We'll assume that transaction 1 finishes first, just for the sake of this demonstration, although it could have been in either order. Transaction 2 will create the row 3 without any problems, but when it gets to row 4, the village of Fonningley in Ostfolk, these are all fake villages, by the way, it will need to take a lock, and so it will take a lock on the existing node, Ostfolk, and it will add the village and the relationship that it needs to add, and then it will release the lock. Next up, transactions 3 and 4 will run, and here we'll have a problem. So both transaction 3 and transaction 4 will need to take a lock on the same node, the same county, and this results in an error that looks like this. So because 2 nodes are simultaneously trying to lock and merge the same node, this is a problem. So the solution here is to use retries. And this is an example here of how you can do that in Cypher, but of course you can do application level retrying as well. So that's all I have for you in importing, but we do have a sneak peek in the last few seconds of this. I can talk about native retries, so making that look a little nicer. We can add parallel runtime support. This is coming soon, perversely only in slotted for now, but soon to be runtime parallel. And finally, of course, there'll be more speedups. And that's everything I have for you. I hope you're having great nodes, and thank you very much. And I hope you enjoy the rest of it.